Okay, welcome back. Happy Friday. Today is March the 4th. We are covering lesson 13. That is monumentous because it's our last lesson before the test. Test is coming up on Wednesday. The coming Monday is our review day. I have no agenda for Monday. I'm not going to come in and say this, that, and the other thing. We're just going to study just like we do when I have no agenda, right? So work on practice problems, make your reference sheet, whatever you want to do. You're going to do on Monday, and then our first test is Wednesday. It is on everything from the semester up to and including what we cover today. And again, it is not too early to start studying for that test. It's on a lot of stuff. Much better to do like 25 minutes a day of studying for 5 days in a row than to try to cram 2 hours the night before. Maybe even better than that would be an hour every day between now and then, but I know you guys are busy. Okay, so let's start on page 104. At the top, daily summary. In this lesson, we continue to look at applications of systems of linear equations. These applications involve mixtures using percentages and travel. These applications are a bit tougher than the ones in our last lesson, but it's going to be the same kind of setup, same kind of process for us. Number one, an auto mechanic keeps bottles of antifreeze. So antifreeze is a liquid that combines two things. A bunch of antifreeze is just water, but the rest of it is a chemical, and that chemical is called glycol. Okay, so when you say the word antifreeze, you are just meaning a combination of glycol, that chemical, with water. That is all. And the only thing that differentiates one bottle of antifreeze from another is the percentage of glycol. You could have a lot of glycol and not too much water. You could have mostly water and just a little bit of glycol. That's the only difference between these different bottles of antifreeze. So this particular auto mechanic has two strengths of antifreeze. The first bottle is 20% glycol, which means what percentage of that bottle is water? 80%, right? It's just glycol with water. And the second bottle is stronger. It is more glycol, 35% glycol. The other 65% is water. Suppose that the mechanic needs to create 12 quarts of antifreeze, which is 25% glycol. So first of all, I'm hoping we buy that that's possible because the 25 happens to live between 20 and 35, right? So it's just going to be a matter of mixing these two things in exactly the right ratio, and we'll be able to build our 12 quarts that has that 25% glycol. How much of each bottle should be in the mixture? Again, if you look carefully, the question itself tells you what the variables should represent. So how much of each bottle? We'll let L equal the amount of antifreeze in quarts. Don't forget unit words. In the 20%, L for low. And then H can be the amount of antifreeze in quarts. In the 35%, H is high. Okay, so we're going to use a table. It's got slightly different row headings and column headings, but it's the same idea. Let's first fill in the percents. Those are the easy ones. What am I putting here in the 20% glycol row? 0.20. Make sure you put your percents, convert them to decimals before you put them in the table. In the next row, 0.35. In our last class, this middle bottom entry, I don't think it had anything in it, in any of the tables we filled in, but it's got an entry here. The final mixture, what's the desired percent? 0.25, that's what we want. So we got to put that in there. That's where it goes. Okay, first column, if we set it up this way, is going to contain our variables. So what letter did we use for the amount of antifreeze? For the 20 was L, and down below, H. And sometimes you're given the number in the final mixture, which we are in this case. How many quarts of antifreeze are we after? 12. 12 quarts of antifreeze. Okay, and we said it before, but we'll say it again. The last column, if you set the table up right, is just the product of the first two columns. I'm hoping you buy it here. The last column represents the amount of glycol. I thought that was the first column. What's the difference between the first column and the last column? Right. The first column includes the water. The last column is just the glycol only, right? They're both number of quarts, but they're different. So antifreeze, remember, is the water with the glycol. Last column is just the glycol only. Well, if 20% of this first bottle is glycol, then 20% of L is how much glycol you have in there. So we're just multiplying, right? 0.20 L. And in the next row, 0.35 L. H, thank you. Thank you. h. And in that last spot, often we were given the number that goes in that last spot in our last class. Here we're not. We have to calculate it, but we got to figure out what to put in there. Well, in the same way that we multiplied here times here and put it here, and this times this and put it here, we're going to multiply this times this and put it here. It's the same calculation. Ultimately, you want 12 quarts, and you want 25% of those quarts to be glycol. So we're just doing 25% of 12. So we'll put it, and we'll do our calculation. 0.25 times 12. And a quarter of 12 is just 3. Sure. 3 of those 12 quarts are supposed to be that chemical glycol. All right. And with the table filled in, writing the equations is pretty straightforward, actually. First equation comes right here. Say it out loud. L plus H equals 12. Last equation comes from over here. Say it out loud. 0.20L plus 0.35H equals 3. It's really tempting. It's really easy to forget that you're supposed to multiply the 0.25 times 12. All the time I see people put the 0.25 here. They just don't know how to handle, like they know the desired thing is 25% and they'll just set it equal to 25%, but that ain't it, right? We need to know how much glycol we have in this case. So we multiply. Okay, so we're not, again, we're not going to solve our equations. They are written down here. Only thing I'll say about them, if you don't like those decimals, you're welcome to multiply that bottom equation by what magic number to get rid of the decimals? 100. If you multiply everything by 100, that 100 distributes, and you get 20L plus 35H equals 300. And so if that equation is friendlier for you to work with, then by all means, get rid of those decimals right off the bat. You can solve it later. The answer is given. Looks like 8 quarts of the 20% and 4 quarts of the 35. Questions on that? Okay. Jeff, does that make the gold problem? Okay. Yeah. Jeff got a jump start on tonight's homework and had some trouble with that last bottom right box. Okay, let's take a look at number 2. A similar approach can be used for problems involving distance, rate, and time. For all such problems, we will use the formula, excuse me, rate times time equals distance. That is not a formula that you necessarily have memorized or have thought about symbolically. It's R times T equals D, but for sure it's something you all know. If you are traveling 60 miles per hour for 3 hours, how far have you gone? 180. For sure, we all know we need to multiply those two things. Multiplying these two things gives you 180 miles. And in fact, that 60 miles an hour is a rate multiplied by the 3 hours, which is the time, to calculate the distance traveled. Good? So that's a formula we all know, even if we don't think of it symbolically. All right, here we go, number 3. Irma flies her plane with the wind and makes a 450-mile trip to Saratoga, New York in 3 hours. The return trip against the wind takes 5 hours. Same distance. We're making a 450-mile trip just out and back. But if you have the wind helping you the whole time, you're going to go faster. And if the wind is working against you, you're going to go slower. So 3 hours and 5 hours, as opposed to same time for both directions. We're going to find the speed of the wind and the speed of the plane in still air. That can't be any clearer in terms of what your variables should be. There they are. The speed of the plane, speed of the wind is one variable, and the speed of the plane in still air is the other. Really easy to neglect units. If you do that, you will lose a point. Don't do that. Miles per hour is the natural unit for these two speeds. Okay, here we go. This next table, again, we're going to fill in the time column. So we've got the top row is the trip to Saratoga, which was with the wind. Return trip was against the wind. Let's fill in the time column. With the wind, how long did it take? 3 hours. Against the wind, 5 hours. Okay, next place we would normally go is that first column, and we would just stick our variables there, right? Like L and H. But that's not what goes there, because the speed of the plane by itself is P, but you can't just put P here and W here. I mean, like somehow we have to figure out what is our like net speed when the wind is helping us, and what's our net speed when the wind is working against us. So it turns out it's really easy once you see a numerical example. Suppose that the plane is traveling, I don't know, 140 miles per hour. And suppose that the wind is 10 miles per hour. When the wind is helping the plane, how fast is the plane really going? 150, yeah, right? If the two of them are working together, the plane's net speed is 150 miles an hour. When the wind is working against the plane, how fast is the plane going? 130, right? Normally it would go 140, but it's losing 10 miles per hour because of that wind. So I'm hoping we buy that when the wind is helping, you just add the plane speed to the wind's speed, and that's what the plane is really doing. And when the wind is working against you, you subtract them. That's it. So let's fill that in our table. With the wind, P plus W. Looks quite different from all the other entries we've put in that column so far. This one has both variables in one slot. Against the wind, P minus W. For all of these kinds of problems, it's a P plus W and a P minus W. There's nothing else it can be. I could change the context a little bit. I could say it's a boat. Typically, boats don't have to work against wind. What might a boat have to work against? The current. So if the boat is with the current, you add the two speeds. If the boat is against the current, you subtract the two speeds. That's it. Okay, last column says distance. Well, we've got our fancy formula here. Rate times time equals distance. Hey, rate is our first column. Time is our second column. If we multiply those two columns, it equals the third column, which is exactly how all our tables have been set up, right? So again, the last column is the product of the first two. So we're just going to write it here. 3 times, note the parentheses, P plus W, just multiplying those two guys. 5 times P minus W. Okay. You could put 450. Yeah, you could put 450 in both of those. And in fact, that's what our equations are going to be, is just making each of these things equals 450. So, yeah. So not wrong to put 450 there, but our convention is just multiply the first two columns and stick it in the last column. But hey, we happen to know the last column is also 450 in this case. So those are our two equations, and you solve them as usual, all right? Okay, there's a couple of common ways to go wrong with these kinds of problems, the plane problems and the boat problems. One of them is to swap the times, 3 and the 5. And if you're not careful, like putting good row entries, like row labels over there, it's really easy to just kind of arbitrarily pick the first thing and put it in the first spot and the second thing in the second spot. And if you're not paying attention, that's going to be wrong half the time. And the reason it is wrong is that here, when you say P plus W, are we talking the slower leg or the faster leg? That's the faster leg because the speeds are adding together, right? They're working together. And the faster leg is going to take more or less time. If you are going faster, is that taking more or less time? Less. And so you cannot just arbitrarily pick what goes here. You got to put the one that's less time with the one that's faster. I don't know if it's something worth memorizing, but definitely you got to pay attention as you put these things in. So 3 and 5 in that order. And the only other common mistake I see is that sometimes instead of this thing right here, P minus W, people put W minus P, and up here W plus P. Now one of them is totally okay. Which one is equivalent to what's already in the box? W plus P. You can add in either order, doesn't change anything. But if you do W minus P, because you just know, oh, I have to add on the one and subtract on the other, you're going to get silly answers. Because W minus P, in this case, with the 140 miles an hour and the 10 miles an hour, tells you that the plane is going negative 130 miles an hour, which it isn't. So you can't just arbitrarily put the W and P in any order. Plane is going faster than the wind, we hope, otherwise we're not making this trip. So always got to put the plane speed first. Any questions on this example? Okay, and again, you can check later on, the answers here are 120 miles an hour for the plane and 30 for the speed of the wind. All right, so on the next page is the answer key, and following that is the activities. We're going to follow the same unusual directions we did last class. I want you to set these guys up, meaning, like fill in a table and write your equations, but then stop instead of solving the equation, move on to the next one, set them all up. That's the important piece for today. You'll have time to go back and start solving them, but I want to make sure you set all of them up for sure.